Good evening, everyone. I welcome you to the third simulation webinar of Solar Decathlon India. I am Yashima and I will be moderating your session today. Today, we will see examples of how to use simulations to analyze passive techniques like building orientation, window to wall ratio, shading, window design, and natural ventilation. You will also learn how to incorporate natural ventilation for a mixed mode operation in Design Builder. Before we begin, I would like to acknowledge the support of the Department of Science and Technology and all our supporters and affiliates. A special thanks to Design Builder for their continuous support to Solar Decathlon India. Today, we have with us Mansi Parikh and PC Thomas. Mansi is a senior sustainability consultant and has key qualifications in the field of passive designing, low energy cooling, and HVAC systems. She has worked on various projects with goals leading to net zero energy, water, and waste. We also have with us PC Thomas, who is the founding director of Team Catalyst and also an adjunct professor at the University of Sydney. He specializes in integrated building design, using simulation tools to assist in the design and delivery of sustainable buildings, in particular in predicting the performance of the mechanical services. He has a master's degree in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. PC is today talking to us from Australia, so it is late evening for him right now. Hi, PC, and hi, Mansi.
Hi.
Hi. Usually we take our questions towards the end of the session, but for today, Mansi has to leave a little bit early, so we'll take questions right after her session. So if you have questions, any questions during Mansi's session, please feel free to send them right away. And after that, we'll have PC's session, followed by another Q&A session. And with that, Mansi, over to you.
Thank you, Yashima. So I'll quickly share my screen and then we'll proceed. Can you see my screen?
Yes, Mansi.
Perfect. All right. So in the beginning of the session, this time we have a question. Should we start with a question, Yashima? Can we start with the polls?
Yes, sure. So the first question today is, what do you consider to be passive design strategies? And the options are A, air conditioning, mechanical ventilation, heating; B, insulation, thermal mass, shading, natural ventilation; C, all of the above; and D, none of the above.
This is going to be an interesting question. So, this session is going to be regarding passive design strategies and how to incorporate them. So let's see how everyone interprets these strategies.
Definitely. All right, we have many answers coming in, and I will now end the poll. Yeah, Mansi, here are our results.
Oh, wow. So most of you got the results correct. So the answer is B, that is insulation, thermal mass, shading, natural ventilation. So, we are not using any sort of active devices like your air conditioning or your other mechanical ventilation system, which would use in term electricity, so that's the reason we did. That's one of the reasons they are called passive design strategies. So that would be your insulation, providing insulation in your walls, providing thermal mass in your walls, or providing shading, adequate shading to reduce the amount of cooling loads or make the buildings and the facades energy efficient. Or strategies like natural ventilation, So in this particular session, we are going to discuss about natural ventilation strategies, how it can be incorporated at at planning level, at the master planning level. Passive design studies using shoebox model for various orientation, window to wall area ratios, and strategies like shading. Design for natural ventilation in buildings during detailed design stage, and wind-driven natural ventilation and window design. So these are the topics which we are going to cover in this presentation. In this presentation, I'll be discussing my findings for projects. For the project which I worked on, that was for Ashoka University, which is going to be a net zero development. The campus is located in Sonipet, Haryana, which falls under temperate climatic conditions. So, the climate is similar to Delhi, which would have both high temperatures during summer months and lower temperatures during the winter months. So we have discussed the climate analysis in our previous, we have also done, we discussed the climate analysis in the previous webinars. So, wind speed and wind direction plays a major role when we are designing for natural ventilation in any particular space or any particular building. So this chart shows the wind direction and speed for 3 specific seasons, which are predominantly seen in India, that is summer, winter, and monsoon. As per the climate analysis done and discussed during session 1, so Delhi, the occupant feel more comfortable with elevated wind speed during high humidity conditions, specifically in monsoon and summer months. That's what you would also have observed, right? When you are walking, specifically when we look into pedestrian comfort. So when you might have been walking during, say, monsoon season or say peak summer, so you would be sweating, right? And then when you feel wind directly on your skin, you would feel a little bit more comfortable. So elevated wind speeds help to improve thermal comfort, specifically during monsoon seasons. So we have a question coming up. Yashima, if you could start the polls.
Yeah. So another question is, clear openings should be placed in which direction to improve pedestrian comfort through natural ventilation in monsoon months? And the options are the 4 cardinal directions: north, south, east, and west.
So you can look into the diagrams, you can look into the chart and then interpret these.
Right. A lot of mixed responses coming here, Mansi.
Interesting. So just for everyone's view, we are asking this question specifically for monsoon months, specifically from July to October. So.
All right. I think let's look at the results now. So I will end the poll. And Mansi, here are the results.
Wow, this is interesting mix of answers. So, roughly 20% of you has said north, south, and east, and 50% has the correct answer, which is west. The answer here is west. Okay, just pointing that out. And I'm going to go back and say why west. So here, what you can see is, this. So the way we look into these charts is that, these are your wind speed. This goes from 0 to 9 meters per second. Okay. And this shows the cardinal direction. So monsoon would have predominantly west winds. Okay. A little bit in northwest north or northwest, very little bit of that here and there, but predominant wind direction is west here, because you have highest wind speeds. You see blood red here. And that is across the, you can see that across the month as well. So maximum wind speed and the highest amount of wind from the west direction. I hope I made this clear. So if you have questions, then you can put that in the chat box and we can discuss. But yeah, so that's the reason why west is the predominant wind direction in monsoon month. Similarly, what you can see in summer, it is across the place. There is a little bit of wind from west, and then there is also southeast, east, and these are the directions. Okay. And for winter months, which we can see, this is basically from this half, from northeast, and east is the predominant wind direction here. So that's how you interpret. Uh, okay. So post this, after looking into which are the prominent wind direction, what we did was we started looking into CFD studies. So this simulation diagram shows the results from CFD. CFD stands for Computational Fluid Dynamics Study, which was done for at the master plan level. This was conducted in Butterfly, which is plugged into Rhino. There are other simulation softwares which you will be able to do CFD studies in, and Design Builder is one of them. So PC will be able to explain you that in detail. So the wind direction considered for this study was west, because we saw that previously. And the legend shows that wind speed from 0 to 5 meter, 0 to 3 meter per second. So you can see 0 is light, darkest blue, and 3 meter per second is almost dark red. Okay. So for wind-driven natural ventilation to work, there has to be negative and positive wind pressure on one side, and on the one and the another side of the wall. What I mean by that is, say for this particular space, okay, there has to be positive wind pressure. And positive wind pressure directly correlates to wind speed. So there has to be higher amount of wind pressure on this side and the lower on this side, which you can see here, predominantly dark red and light orange to blue, that is 1.5 to 1 meter per second. This is going to be 3 meter per second. So there is going to be a difference in wind pressure, and that's the reason this space can have better natural ventilation if the openings are provided, which are sufficient. So we have cut this section at 1.8 meter per second, 1.8 meter above the ground level, which is basically your pedestrian comfort. So humans feel comfortable at this particular stage because we feel wind at 1.8 meters per second, considering the height, average human height. So for a few spaces, there are low pressure zones which are formed on both sides of the building. So say a building like this, it has low pressure zones from this side as well as this side, because this is almost 0 meter per second because of the shape of the courtyard, and this is also a very less wind speed of 0.8 meter per second. So there is not enough pressure difference which is going to be created. So what we suggested was to improve natural ventilation in this particular space. We suggested to provide passageways. Okay, provide passageways here, and opening is suggested to improve pedestrian levels in these particular courtyards. So there are going to be food courts which are going to come in, which are going to be naturally ventilated. So what we suggested, this space is going to be ideal, enough span, as well as it's going to be better in terms of natural ventilation, because ideal pressure difference. The next is, we cut the section at 5 meter per second. At 5 meters above the ground level. 5 meters is ideally the first floor. Okay, so based on so this was proposed. So this was going to be a proposed utility block. Okay, so this would house functions like organic waste composter, diesel generator, etc. So since it is in windward direction, it was recommended to relocate it into a different position, because that smell can be carried around in the whole campus. So those are the kind of inferences which we derive from these studies. So and also these they suggested dining block and the gym here. So it was proposed to provide sort of a breezeway to improve the natural ventilation in these particular spaces. So these are the sort of inferences which we derived, and we suggested it to the client. So that is natural ventilation studies. The next step for us was, once we have passive design strategies which were selected, post-climate data analysis, which we discussed in the session 1. We started looking to studies for orientation, shading, window to wall area ratio, and conducted the impact analysis of these principles. So and that also, these studies help to explain client and architects the impact of these strategies in the design process. So this chart shows annual cooling loads on the y-axis here. Okay, and then these are various orientations like northeast, southwest, northwest and southeast, north and south, and east and west. Okay, and these are your annual cooling loads. So we studied the impact of orientation in terms of annual cooling loads. So Yashima, we have a question coming up. If you could start the polls.
Yes. So our next question is, as per the graph above, or the one on your screen, which is the most energy efficient orientation for your building? And the three options are northwest/southeast. Second option is north/south. And the third option is east/west. All right, we've got many responses. Another 5 seconds and I will close the poll. All right, I will now close the poll. And Mansi, here are our results.
Interesting. So, okay, so the answer here is east-west. Okay, why east-west is simple. You have maximum amount of annual cooling savings in this particular case. So it was found that east-west longer axis gave maximum amount of annual cooling load savings, that is almost 1.36%. Hence, it was proposed to the client to orient maximum buildings as possible on the whole site with east-west longer axis to reduce energy consumption. So because annual cooling loads is directly related to annual energy consumption. Okay, so for once we had this done, for east-west longer axis, once we freezed that particular orientation, what we started looking into was window to wall area ratio, window to wall area studies. So to dive into the optimum WWR to reduce energy consumption in the air conditioned spaces. Okay, window to wall area ratio for a facade can be calculated by dividing total window area with the total wall area. Okay, 4 cases are studied here. The case 1 being 60% WWR, case 2 being 50% WWR, case 3 with 40%, and case 4 with 30% WWR. And you can look in the y-axis has annual cooling loads in kWh, and these are the percentage savings for all of these cases. Yashima, can we launch the poll?
Yes. All right, next poll is, as per the graph on the screen, which is the most energy efficient window to wall ratio for the building? And the options are 60%, 50%, 40%, and 30%.
Okay, before we jump into this, once you are answering these questions, I would like to say, so how do you derive annual cooling loads in a building? So when you simulate, there are a couple of results which you get. One being annual cooling load. Okay, then there is peak cooling load. Then there is going to be annual energy consumption. Okay, these are some of the result format which you will get. Okay, here I have considered annual cooling load because I wanted to look into the impact which would have in terms of HVAC systems, or say in terms of only cooling of the whole building. As you can see that, when we look into the overall pie chart of the annual energy consumption of a particular building for buildings like residential, or specifically in terms of office buildings or these academic buildings, almost 50% of the total energy consumed is for HVAC systems. Okay, so that was the reason why I started looking into the annual cooling load as a matrix to check all of these parameters like shading or WWR or orientation.
Mansi, just a quick thing. So we have a question. What is the percentage in red color? What does it signify? Could you answer that?
Absolutely.
Yeah.
So this is what I have done in all of these cases. We require a base case, okay, to check how other cases are performing as compared to one particular case. So say for example here, 60% is the base case and 5% is reduction in the annual cooling load as compared to the base case. So as you can see, for WWR 60%, it is roughly around 2,05,000 is your annual cooling load. And at WWR 50%, your annual cooling load is somewhere around 1,98,000 kWh. So what I did was simply calculated the difference between the same, and that is converted into terms of percentage. So simply 5%, the way you get 5% is 2,05,000 minus 1,95,000, which is for 50%, and then you divide it again by the base case consumption. So this is reduction in terms of percentage as compared to the base case. So this is compared to 50% is compared to 60%, 40% is again compared to 60%, and 30% here is compared again to the base case, that is 60%. So 14 is the difference in terms of annual cooling load reduction as compared to the base case of 60%. I hope I answered that question.
Yeah, thanks, Mansi.
Now we like to look into the poll results.
Oh, I had not entered the poll. All right. All right. I've entered the poll now, and here are the results.
Perfect. Most of you are saying that, all right. So most of you here are saying that answer is going to be 30%, because it has highest amount, so in terms of reduction, it gives highest amount of reduction in terms of annual cooling load. You could see that here in this particular case, that here it is reducing the energy annual cooling load, and in turn reduce an overall energy consumption by roughly around 14%. So we recommended 30% of window to wall area ratio to a client. So after the wall to window area ratio studies, we started looking into optimize for shading devices for this particular building. So this study assisted in showing the clients and architects importance of shading devices in reducing the energy consumption. So 4 cases were studied. 4 cases were studied for east-west longer axis case with 30% WWR. Why I'm saying that, we started first with the orientation, then we started looking into WWR, and the next step was to understand the shading devices. So all of this is on top of each other, So there are 4 cases which we studied. The first was the base case, which has no shading device. The case 2 was horizontal shading device with 1 feet of depth. The second was 2 feet depth shading device. The case 3 was shading device with 3 feet of depth. So Yashima, we have a question coming up, if you could.
Yes. Yeah, Mansi. So our last question also is, as per the graph on the screen, which is the most energy efficient horizontal shading device? And the options are the 3 cases: 1 feet shading, 2 feet shading, and 3 feet shading.
Yes. So shading devices are important. Okay. Shading. So your chhajjas, initially in the previous or the probably pole houses, what you observe, or probably traditional houses had chhajjas to protect windows from rain, to protect windows from direct sunlight. Now these shading devices, modern day shading devices, have various similar solutions, or they provide similar solutions for protecting against the rain, protecting against the direct sunlight, protecting against the glare issues or glare probabilities into particular spaces. So all of that. So you might have observed, if you sit right next to a window, you might have observed veiling glares, or probably one of you would have seen that, right? When we are sitting on working on a desktop right next to a window, you would across the day, if there is not a proper shading provided, then you will be feeling a veiling glare coming up on your screen, and that probably will be blinding for some part of the day, probably during the evenings or in the mornings, based on the orientation of the window, or where exactly you are sitting. So the shading devices are must in those spaces, and they
Yep.
help
Yes.
in quite a bit of ways.
Yeah. All right. I will now end the poll so that we can also look at the results. Mansi, the results on your screen.
Absolutely brilliant. So the answer here is the 3-feet shading devices. Okay. The answer here is the 3-feet shading devices because they provide the maximum amount of reduction in annual cooling load. However, in this particular case, it was found that case with 3-feet shading was found optimum for WR and the orientation. However, the difference in energy consumption between both the cases, that is 2-feet shading and 3-feet shading, was roughly around 0.6%, was not very much. And also 2-feet shading device, we suggested this to client only because, it is easier to do 2-feet shading devices. Okay, providing 3-feet long shading device for a particular window was very difficult, and it would require a lot of designing from the clients, and then the architects were not ready to take that up. So in this particular case, the difference between both the cases was not very much, not very significant. So that was the reason we suggested 2-feet shading devices to the client here. So there are possibilities that there will be a lot of back and forth, and then whatever you say out to the clients or the architects, and they might not take things up, and then you find a middle ground and then proceed. So post that, after we are going to discuss alterations for natural ventilation in facades. So this is the design for academic block where the courtyards were conditioned across a year. So CFD studies were done for internal spaces to understand the wind flow in the particular spaces. So and this study was conducted with wind speed of 3 meters per second from west direction, as you've seen earlier, and this was decided based on the climate studies. So these balcony spaces had with 80% of openings, and corridors were opened from both of these sides. So these were naturally ventilated spaces specifically, and the corridors were also naturally ventilated. So in the legend, 3 shows maximum wind speed and 0 is the least amount of wind speed. So few patches in the balcony and courtyard has little to almost as you can see, it has little to almost no wind speed. So these spaces are going to be naturally ventilated, and you can see that this has very little wind speed and wind movement specifically. So we had to specify certain alterations to the design to improve the wind inside the spaces, to improve the wind and improve the natural ventilation in these spaces. So these are a couple of changes which we suggested. One was filleting this particular corners, or splaying this to generate sort of a funneling effect. Okay, there is going to be a window here, and then we said probably splaying this would improve the wind speed and the wind movement. We increase the wind depth of these particular opening, increase the width of this opening to 2.5 meters, filleting inner walls if possible, and smoothing the niches to get the continuous wall surfaces, and having these curves, diagonal curves, to improve the wind movement in the spaces. So we suggested, what we did was, next step for us was we saw that, if we make these changes, there is going to be a change in wind movement in the space. We conducted one more wind study. Okay, so this is the base case, which has, there is no, this is the case directly we got from client. And then what we did was we started incorporating these changes here. You can see these changes. here, as I showed in the previous slide. And what we observed was there was improvement in the wind movement in these particular spaces. As you can see, this has dark blue sections. So the dark blue sections is almost 0 to very less wind speeds. That was improved to almost light blue sections. So 1 to 1.5 meter per second of wind speeds here in these corridors, as well as these outdoor spaces. So we suggested these changes to the client and got it approved. And so we improving these, adding those small changes, improve the wind movement in this particular scenario. So so once we have decided on once we made those small changes in terms of in the internal layouts of the building, there has to be a way to improve the window opening sizing. So this study was done for dining area to optimize the window openable area. The dining area here is naturally ventilated across the year. So we studied two cases, the case 1 and case 2. The case 1 has, this is case 1, which has windows are 100% openable, say windows like side hung windows. And the case 2 here has windows which are operable for 50% percentage of opening, like sliding windows. And what we started looking was the discomfort hours. So and the annual hours where the ambient temperatures were going above 33 degrees was calculated. And the above 33 degrees C is the upper limit for natural ventilated spaces in Delhi. This was taken from India Model for Thermal Comfort. To understand this in detail, you could visit self-learning modules. So case 1 has 100% of openable windows like side hung windows. Case 2 has 50% of opening like sliding windows. And as you can see that, discomfort hours, and these are discomfort hours. Percentage, what you see are discomfort hours. Those are the hours where the temperatures are more than 33 degrees centigrade across the year. And it was observed that 15 to 25% increase in discomfort hours was observed with windows with 50% clear openings, where say for sliding windows. As you can see here, it is 10%. It is increasing to 18%. Okay, discomfort. So basically, discomfort hours are increasing in all of these cases. So we proposed 100% openable windows, so side hung windows in this particular case. So this is how you actually do the window sizing and compare two cases to understand what you would like to propose to the client as well. So this is how we proceeded on this one. And I think we are towards the end of our presentation, and thank you. And I will be open to take questions now.
Thanks, Mansi. Yeah, so I'll quickly take a few questions that we've got so far. The first question is, allowing ventilation along the wind direction will also increase windows exposure to the rain. What should we do in that case?
Okay, so so that's the reason, right? Any window which you provide, probably in north, south, west, or east direction, more or less, you will have to provide a shading device to it. There can't be windows, more or less, which won't have any sort of shading device. Shading device also at times acts as a protection device against, against your drains. So similarly, I would say that you would require shading device. I understand you are increasing your exposure towards the rain. However, you would have to provide shading device to mitigate, to mitigate exposure in terms of daylight or for glare issues as well, right? So, yeah.
Right. Thanks, Mansi. Next question. In the WWR comparison chart, how was the base case decided?
Okay, so ideally, from my experience, the highest amount of WWR, window to wall area ratio, would have highest amount of energy consumption, because you are increasing the window exposure because you are increasing the window exposure in a building. That again, once you start providing glazing, it would have thermal heat transfer through two mediums. One is through conduction and the other is through radiation. Okay, so that was the reason which I was sure that 60% would have highest amount of annual cooling loads. So that's the reason. That's how we selected the pay scales on that one.
Right, but does it also have to do with any standard, Mansi, like NBC or ECBC, for example?
Yes. So ECBC talks about restricting WWR to less than, say, 40% or so. Griha talks about restricting WR to less than 40%. So yeah, you could consider those cases as well.
Okay. Yeah, thanks. All right, next question. Comparison between various orientations and its load calculation. That's the question is about that piece. Can it be done in Climate Studio / Butterfly plugin for Rhino, or can it be only done in Design Builder?
It can be done on all of these softwares actually. Okay.
Right.
So because we are looking into load reduction, so load calculation. So any simulation software will be able to help you in all of these. So yeah, you won't be able to do that in Butterfly, which is plug into Rhino. Butterfly is specifically and predominantly for CFD studies. For this, you will have to use Honeybee and Ironbug, which would help you in terms of energy modeling. So absolutely, you'll be able to do that in Design Builder. So
right. Thanks, Mansi. How did you calculate the annual cooling load? Next question.
Yeah. So how do you calculate annual cooling load in Design Builder? So that's PC probably in his session, he can show that how to get the annual cooling load, how to look into this.
Actually, I think that would be helpful. Yeah, because there are a couple of questions about where do you get the cooling load in Design Builder. So PC, probably, if you could show that to the students.
Okay, we'll see how we go for time. If not this session, another session, definitely.
Sure. Yeah. All right. Thanks, PC. All right. Next question. So based on the conversation that we had around the WWR today, the question says, do you mean to say that 100% openings are better? But then what about the heat gain in buildings?
So okay, so I think that is a combination between the naturally ventilated and air-conditioned spaces. So when I was discussing in this presentation, couple of the spaces, specifically like corridors, or the last slide which I showed you, that was dining hall, that was naturally ventilated. Okay, and the other spaces like classrooms or offices were air conditioned. Okay, so when I say that for air conditioned spaces, 100% there can be openings because there can be natural ventilation and there can be openings. But for certain spaces, okay, we have to look into studies like discomfort hours to arrive at the result saying that if 100% openings are better or not. Because we have to look into the hours and across the year which we are going to naturally ventilate this space. So for specifically like dining hall, which was in a city like Delhi, winters are going to be comfortable, correct? What you are going to do is you have to look into discomfort as for monsoon and only summer months. Winters are going to be more or less comfortable. Some months of monsoon are also going to be comfortable. Specifically, we have to look into the summer months. So during those times, elevated wind speed helps to reduce the discomfort. It also takes out the heat in a particular space, and if it is the cross ventilation is done correct. So hence that was the reason we said 100% openings was better. Also, we are not in this particular space. What we did was we started looking, I've not shown that here, but what we did was we started looking into what happens during, say, breakfast, lunch and dinner. So what percent should be open in breakfast, lunch and dinner, and probably we did, and after that we optimized, and based on that we have the algorithms set for the openings to be designed accordingly. So there's a lot of details which goes post this as well when we do this.
Right. Yeah. Thanks, Mansi. All right. I'll take one last question. Looking at the case, which is Ashoka University, the north face exposure throughout the year, for this side? If so, what is a good example, Mansi?
Yeah, so you're saying that north faces seem to have least minimum solar radiation and daylight exposure throughout the year. Spaces like that, then that mean that if it is less solar exposure across the year, you do the irradiation studies. If it is less, if if it is less than 250 or so, then it is all right. You don't have to provide shading devices accordingly, because any which ways irradiation is less on that facade. So can go do away with it. So there are certain spaces which will have sort of mutual shadings, and there you don't need to provide shading devices.
Right. I think when the students do irradiation studies, they should also be looking at glare. If there is direct glare, I think in that case, shading device has to be provided. Because otherwise it leads to a lot of discomfort.
Absolutely.
Right. Yeah.
Absolutely.
All right. I think, yeah. All right. I think that's all the questions I think we can take for now, because we're kind of short on time as well. The remaining questions, a few are about Design Builder. We can pick them up after PC session. Thank you so much, Mansi, for your session today. And we will see you next time in December, probably, for your next session. Thanks, Mansi.
Thank you. Thank you.
Bye, Mansi.
Bye, PC. Thank you.
Bye. All right.
I think we lost you for a short while there, Yashina. Are you back there? We lost your vocal, lost your audio for a second.
Am I audible, PC?
Yeah.
Oh, okay. You can begin sharing your screen, PC.
Okay, thank you. Okay. So am I good to go?
Yes.
Okay, so Mansi has covered many topics. So she has fitted in 20 minutes, I think, almost a full semester worth of architectural training. So what we'll do is we'll only look at one part of it today. And today I'll try and concentrate on how you can look at doing natural ventilation analysis in Design Builder. And on another day, we can look at cooling loads, okay? Because there's some differences in the way you analyze them. When you look at when you're looking for cooling load, then you're assuming that there is some heat to be extracted from a hot place. You can do that in air-conditioned buildings, and therefore the way you analyze that is a little bit different. When you're looking at naturally ventilated spaces, you're making the assumption that you're not putting any mechanical devices in there. So you don't have an air conditioner, you don't have fans, you know, when I mean fans, I don't mean ceiling fans. You can combine ceiling fans with air conditioning. In fact, the thinking nowadays is that you should. But right now, let's look at it only in terms of how we're looking at natural ventilation. So I've got this fairly simple model to look at. And what I've done is there's two floors. There's a ground floor and there is a first floor that have been set up. They have identical floor plates, and they're quite simple in the way that they're set up. But it's useful because we can see a number of outputs and look at how they work. Now, the first thing probably to do is to maybe look at how the building is set up. So in this view, you can identify what are the materials you have put on, okay? So what I've done is I have two kinds of glazing that I put up just to make it different. So the performance of the glazing for the windows is different. Now, the performance of the glazing will impact how heat gain comes through a space. So if we maybe have a quick look, let me just spend 2 or 3 minutes on this because it's quite important. When we look at glazing, talk about two kinds of values for performance. Okay, let me pick this up. So we talk about having solar performance, how much sunlight comes in. We talk about daylight, and they are different. Sunlight brings energy, daylight brings visible light. And then we talk about thermal. So a temperature differential across a piece of glass will mean that there will be conduction, convection across the glass. So if you look at solar, we use this variable called the solar heat gain coefficient of a piece of glass. And if you look at this diagram, when we say that a piece of glass has got a solar heat gain coefficient of, say, 0.71, that means that 71% of the solar energy that hits the glass when the radiation is perpendicular to the glass comes through it. So I've got an example here. If you've got 800 watts per meter squared of solar radiation, the solar heat gain coefficient is 0.7. The window area is 2 meters squared. If you multiply it through, you can see that there is 1,000 watts coming through the window all the time. Okay? 1,000 watts per second. It's joules per second energy. If you think about daylight, then you have to then compare what a piece of glass can do, both in terms of the thermal and the visible light. Okay, so there are two pieces of glass here. They allow almost exactly the same amount of solar radiation, 54% here, 55% there, but they allow very different amounts of light. So you can tune your glazing. Modern glazing is really good. You can tune your glazing to either have more daylight or less daylight. You don't want too much daylight. You don't want too little daylight. How do you decide what is little or not? That's when all the daylighting calculations come in. And in Design Builder, you have radiance built in, and you can do daylighting calculations with that. If you remember, Yashima's talking about glare. So there are 2 or 3 different kinds of daylighting calculations built into Design Builder. If you go in there and you search, see, I'm just going to open this help file for Design Builder. If you go in and search for daylighting, you will see that there are different kinds of daylighting studies that you can do. This one, okay? It tells you that there are 3 kinds. The ones you're looking for, where you can combine looking at both glare, it's probably the best one is this UDI. And if you look up ECBC, ECBC actually gives you some idea of what to look for good daylighting. Okay, so I'm going to leave it there. All right, now let's keep going about glass. The last bit about glass is this thermal transmittance, and you already know about U values. So, you know, depending on what the temperature is inside and outside, what is the glass area, this U value decides how much heat is coming through. So this temperature differential then becomes very important. Okay? So depending on which climate you are, kind of need to think about what is more important. Is it managing solar radiation, or is it managing heat gain or heat loss because of U values? Okay, so I'm going to leave it at that, but let's go back here. In this other view, this is where you can get some idea of, in your location, how does the sun work? Okay, so this I think is Bangalore. So in Bangalore, as you can see, if it is winter, December, January, the sun is much, you can say, lower in the sky. And therefore, when you look at it at different times of the day, this is now 12 noon. If you look at it and have a, say, a look like that, you get an idea of where the sun is coming through the window and impacting the space. Now, I'll let you have a play with that and figure out what to do. I won't spend too much time on that. Okay? What I've done is to give you an idea of how we can do an analysis for natural ventilation. I've got a building here which is completely uninsulated. So it has got a concrete block wall. It has got some very poor performing single clear glass. So if I look at the numbers for that, the U value is quite poor. Okay, so about almost 6 watts a meter squared. And the solar heat gain coefficient is very large, so it allows a lot of solar gain to come through. Okay, and so also does it allow a lot of light. But that's a good base case. Then you can keep improving from that. Now, to make this run in natural ventilation, there are 2 or 3 things to do. But the main one is that you go to the building level, and on this HVAC tab, you make sure that you have ticked the natural ventilation tab. Okay? And I also suggest that you go into the help file for Design Builder, look up natural ventilation, and there's quite a few bits and pieces about how natural ventilation should work, or how you can get it to work. There's quite a few controls that you can use. I'm going to show you something really simple today, so you get an idea of how to use it. And what you're really interested in is using the calculated natural ventilation, not the scheduled one, because the scheduled one really just allows you to specify amount of air, and that's really not what you want to do. You want to find out how much air is coming through because you've opened the windows by a particular percentage. Okay, so back here, I've set up this. Then on your model options tab, you have to change this slider for natural ventilation from scheduled to calculate. Once you do that, the model knows that it's going to calculate the amount of air flowing through the windows And when you go to the openings tab, it will give you these options. It'll give you an operation schedule, and it will give you some amount of glazing that you can open. So what I've done here is just for us to test. I've kept the windows open quite a lot. But what I've done is, again, to maybe make you guys understand a bit, I've written an interesting schedule. So we're going to look at the month of March. And the reason we're going to do that is because March is kind of not really too hot, not really too cold. So you expect that natural ventilation will be quite effective in that month. And till the 15th of March, I've got the windows open 24/7, always open. After the 15th of March, I've opened the windows from midnight to 6 o'clock in the morning, kept it closed till 6 p.m., and then opened it again. Okay, therefore you can write interesting control schedules like that. Okay, so let's do one thing. Let's now run this energy simulation for that month. Okay, so I'm going to run it from 1st March to 31st March. And because it's quite a simple model, it should run pretty quick. But as your models get more complicated, obviously it'll take longer to analyze. So one of the things I suggest to you is try whatever you want to try on a simple one, maybe 2-zone type model. When you are sure that everything's working correctly, then you put it onto a bigger model, because then it's easy to diagnose what's going wrong in smaller models. Anyway, here it's loading up the results. And by looking at some results, we can make some judgments. Then we can go back and look at in more detail at more results. So the first thing that I want to, okay, you can see these arrows here. That's just on March, on 9th of March at 2 o'clock in the afternoon. This is how the natural ventilation is working in the building. You can see here the black arrow is facing north. The wind direction is here in red. This is the wind speed, 1.9 meters per second, taken from the weather file. And because of the direction of the wind, you can see here blue is entering the windows and red is exiting these windows. And you can even see how much air in liters per second is going through the. But it's a nice to have, good looking kind of exercise. But what you're really interested in is how does it work? Okay. So if I look at all these squiggles, let's start looking at some of these zones. So here is the ground floor living. Okay. And if you look at the ground floor living, what you're going to notice is that this dark blue line, which is the outside temperature, say here it is 32 degrees centigrade. The room is actually cooler than 32 degrees centigrade. So because you can see that the air temperature is kind of following the outside temperature. That's because your windows are open, okay? And if you look carefully, after the 15th of March, you can see it changes. Okay? You can see that there are all these squiggles that are being incorporated, and that's because we have shut the window
during certain times. Okay. And you can, if you look carefully here, you can also see the amount of natural ventilation during the day. That sort of changes here. There are many more still periods when the windows are closed. Why I wanted to show you this was, if you look in this one, you can see that the inside temperature is less than the outside temperature. But if I go to the first floor, same room on the first floor, actually the thing completely changes around. You will see that the outside temperature is 31, but the inside temperature is now much higher. It's 33, 34 degrees. And that's because now you have solar radiation hitting the roof of the first floor. That's heating up the space, and the natural ventilation is not effective enough in keeping the temperatures down. Okay. And here, after the 15th, it's much more obvious how the natural ventilation rate has changed, because we are keeping the windows closed during the day. Now, within design builder, it's actually quite interesting. You can go to any particular wall. You can pick the window on that wall, and you can see what's happening on that window itself. Okay. Now, you can see here that you can barely see where the green line is. So the inside surface and the external surface of the window are exactly the same temperature, because it's only a 6mm piece of thin glass. It's clear glass. There's no reason for you to expect any differences. If you were using a high performance piece of glazing, which was double glazed, then you'll see differences there. It tells you what's happening in terms of how much solar radiation's hitting the window, how much is going through, etc. What percentage of that window is sunlit at what time. And then these blue and red lines are very useful. The blue lines tell you that it's airflow coming into the building, and the red lines tell you that it's the airflow going out of the building. So this particular window is acting more as a window with air coming in. Okay. And this is at an east facing window because it's 90 degrees. If you pick a west facing window, maybe it might be different. I'm not sure. We'll find out. So here you can see most of these windows are, this window is mostly airflow going out. So, my thinking was correct. But of course, that will depend on how the geometry of the building is. Okay, so you have these options available to you. And by changing some of these things, you can start to look at how you can improve the performance of the building. When you're looking at naturally ventilated spaces, you're not looking at cooling loads. You're looking for how do you maintain comfort within the space during certain times. So another way of looking at it is you can go to this summary tab. There'll be a series of searchable reports. These are reports that Energy Plus develops. And you can look at, I think somewhere here I've got some temperature distributions. Okay, let me find it for you. So these are the results when they are shown by the design builder interface. But what the design builder interface does is it actually picks up the results that are generated by the calculation engine, which is Energy Plus. So if you look at that folder, you can see my timestamp is 11:28. My time here is 11:36. So we did this run about 8 minutes ago. This file here, which is that HTML file, is the same one that you saw in the summary. Okay. And if you look here, you can see that I asked it to give me the temperatures in each space. So there is a air temperature, there is an operative temperature, there's a radiant temperature. If I look at the first floor living room area, it gives me a bin and it tells me at what time. So you'll see here month of March, and you can see here between 20 and 21, there was about half an hour. And say between 28 and 29, there were about 56 hours. And the total number of hours in that month, which is 31 times 24, is 744 hours. And in that month, there were 227 hours, if you will, that were more than 32 degrees. So you get lots of information from here. And because we ran it only for that month, you even get an idea of when these temperature bins were achieved. So at what time? So, here we go. So 9 o'clock to 10 o'clock. These were a number of hours in particular bin range. So these are quite useful things for you to try and figure out how well or how badly your building is performing. Okay. One other thing I'll show you, that is that we've got this here. So what I'm going to do is these two files, which are the result files, I'm going to call this our base case. So let me copy this and put them away somewhere else. Okay. So what I'll do is I will create a new folder for 2022 and paste these two here. And I'm going to call this our base case. So this is where we are starting from. Okay. And just to give you an idea, if I open that ESO file and look for hourly results, or what I'm going to call zone temperatures. Yeah. So I have zone mean air temperatures, I have zone radiant temperatures, zone operative temperatures. So the operative temperature is like an average between the air temperature and the radiant
PC,
temperature. Yeah.
I think your voice is not coming clearly. So can you bring the mic closer?
Is this better?
Yeah, sounds good.
Okay.
Yeah, thanks.
Thank you. Yeah. So let me try and hook this over my ears so I don't have to keep holding it. How's that? Is that better?
Yeah, this is good.
Okay. Looks a
Thanks.
bit funny, I'm sure, but that'll do. Okay. So I'm going to plot this guy, which is the operative temperature for the living room first floor. And then I'm going to do the same for the living room on the ground floor. Okay. So you can see the difference between the ground floor and the first floor. The first floor is much warmer than the ground floor. And if I also plot the outside temperature, then it gives us a good idea of what's going on. Okay. So the green line is the outside temperature. Let's take these 3 days, which are quite warm. So side outdoor temperature, 32 degrees, 33 degrees, 34 degrees. Okay. So if I plot here, see that. So on this day, in the afternoon, it's 39 degrees operative temperature on that first floor. Outside temperature is 33. Inside temperature on the ground floor is less than that. Okay. So it shows you how much the top floor is doing for shading the ground floor. Okay. So what shall we do to improve this situation? Does anybody want to try a assessment? what should we do to make this more comfortable, this building? Anyone? Nobody? There are many options to make it more comfortable. Is there anything that we can try? Okay, let's do one thing. Let's put some insulation on the roof. That can help, okay? Or we can put some shading devices on the windows. That could help. So we'll try a couple of things just to show you how something simple can improve the performance. So what I'm going to do here is I'm going to do something really, which in architectural terms, it can be quite simple, but it's easy to show how effective it is. Okay. So bear with me while I do this. I'm going to create 1 meter high block. I'll show you. It's what we call a component block, but I'm going to use it as a device to do something easy because I'm not a very good CAD person. Okay. You guys can do much better than me. So I'm going to create a second one. Okay. Now, so effectively what I've done is I've created a shade on the top of the roof. Okay. That's all I've done. I have not changed any window types. I've not changed any opening of the window. I've not insulated anything. All I've done is shaded the roof. The reason I want to do that is if I look at it from in terms of the sun, and I look at it in the month of March. Okay, so I'll pull it to March. You can see that it is quite effective as shading the roof. So what I'm hoping is that shading the roof will bring down the temperature of this first floor, which will also mean there'll be an effect on the ground floor. So let's see if my theory is correct. Okay. So I'm going to rerun that simulation and we will find those results and plot them. So here we go. Again, I'm going to do exactly the same thing. And there are other things you can do. Now, many of the strategies that Mansi has showed you, you can try. Okay? But when you try it on a whole building, some won't work as well as when they do in theory. Okay, so we are going to try this, something that I know will work for the whole building. But of course, when you are looking at your building in entirety, then you can try so many other things. If the building that I had a lot of windows, then I would try to either shade the windows or improve the performance of the building windows or reduce the window to wall ratio. So many options are available. But when you are doing real buildings, you need to kind of look at specifics on that building. While this is happening, I can show you a building that we were working on for in one of our projects. Okay, and we were looking at a very big tower building. So here's the model of the building. And what we had to do was we had curved windows And for the curved windows, you couldn't find high performance windows similar to what you could where the flat windows were. So you can see here, for the curved glass, solar heat gain coefficient was 0.4. Well, for these other dark blue glazing, the solar heat gain coefficient was as low as 0.21. Okay. Then we were interested in studying the building in context. So you can see here it was surrounded by larger towers. We were looking at how does it work. So what we found was that in early morning, there was 1 hour when the sun kind of just got through and irradiated this part of the floor slab. And you can see that here. So we knew that this could be an issue for comfort. Later on, if you look in the afternoon, you found that in summer when the sun was really high in the sky, there was solar radiation irradiating these two facades. And again, if you looked at it, you could see that it was these floors that were not covered by the buildings surrounding it. So we were looking at these options. Okay. Now, when you're doing real buildings, you have to zone the floors. So this floor is zoned. You know, there are different air conditioning systems that are looking after different areas. You can see which air handling unit is conditioning which zone. Okay. Then for us, we were testing the performance of the comfort in those zones. So with Design Builder, we have actually created some options for us to do these tests. Let me show you the output that we created. Okay. So we were looking at two things. One is, does the temperature in the zones, is it maintained? And you can see here, it's doing a check and it's all these zones it's looking at and it's found that it's passed. You can see there's a few hours that are not there, but because we're looking for about 98% of time for this to be passed, it works. Okay. The second thing we are looking at is, does it maintain a PMV of -1 to +1? That's thermal comfort. Okay. Again, it flicks through each zone. We took the results for each zone. And as we went through, we noticed that there were a few zones, and they were exactly the same zones that we had identified where the sun would cause a problem. Those zones were having difficulty meeting thermal comfort requirements. So you can do quite sophisticated analysis. Obviously, there's a lot of work to be done, but you can do that sort of analysis here. Okay, so we have rerun this, and probably the easiest thing to do is go find those results. So I'll do that again. Copy these results. You can see that these results files are always got the same name, so they get overwritten every time you make a run. You can look at something called Simulation Manager in Design Builder that will show you how to do multiple runs. Okay, but for the present, we will just do these two. Put this here, and in this case, I'm going to call this shaded. So we'll call this roof shade. Okay, and then I'll go back here, and what I want to do is I want to open that second set of results as well. So in my SDI training, here's my roof shade results. And by the way, you can lift up as many results as you want, as long as your computer has enough memory. So you can see here I've got the base case results, and I've got the roof shading results. Okay, so let me try and plot this. So I'm going to, I know that the fourth line is in yellow, so I'm going to get rid of it by plotting something I don't need. I can barely see that. And then I'm going to go and plot those two operative temperatures again. So here is my first floor living area. And here is my ground floor living area. And what I want to do is to see whether we have improved the situation by putting the shading. So let me go so it's a little bit easier to see. And let's pick one of those days again. So you remember we had the really hot day and the temperatures were where they were. So let's quickly check. Okay. The first floor with the shading is this purple line. And the first floor without the shading is this blue line. So see what we've done. We have managed to drop the temperature from 39 to 33, 6 degrees relief in operative temperatures. What happened to the ground floor? So the base case is 33 degrees and the roof shaded case is 32 degrees. So again, we have dropped it by more than 1 degree centigrade. Obviously, this is, it's quite a simplified case, but you have to start thinking about how to use it. Okay, so that's kind of a quick lesson in how natural ventilation works using Design Builder. And obviously, you can review certain hours by looking at this data visualization tab. And depending on which day and which time you're looking at, you can actually see the wind speeds. Okay, this will give you some really good indications of what's going on. So this is 5 o'clock in the morning on the 14th of March. There is 2 meters per second wind speed. You can see the blue and the red arrow. You can also see this black arrow, and that's really because I made a hole in the floor slab on the floor that is connecting the ground and the first floor. And this black arrow tells you that there's a lot of air coming up that floor slab. Say you have a staircase, and that's the air that's moving due to natural ventilation through the building. Okay, so I will leave natural ventilation there. And if there are any specific questions to that, please put them on the chat. I can see that there are many questions you have. I'll ask Yashima to moderate that, and whichever one she chooses, I'm
Sure.
happy to try and answer.
Yeah. So, PC, is there something more that you would want to cover today, or that this is?
How are we going for time?
We are slightly over, but depends
Slightly
on
over.
what more you would want to cover. Depends on that.
Because there seemed to be a lot of interest in load,
Yes. Yes.
and we could certainly do that, but it will, you can't do it in, I'll need 45 minutes to do that, or half an hour at least. So that's,
Yeah. I think
yeah.
we have a separate session. The next session would be on HVAC, right sizing, and load.
Loads,
So
yeah, then we can look at
we
all of
could
those
probably
things.
cover that.
Yeah.
Yes.
Yeah.
Yeah. All
So
right.
the only thing that I can say is that, you have options to improve the building by looking at, say, suppose you want to change construction. Okay. Then what you do is you go in there and you pick a construction, or you change your construction so that it is a improvement. So in this case, it's uninsulated. If I add insulation, then it will improve the building. So now my construction has gone from an uninsulated concrete block wall to one which has got insulation. I put the insulation on the outside. So what it does is then it allows the thermal mass to be cool on the inside, and the insulation keeps the heat out of the building. And you can try what happens there. You can change the roof construction, and that will have quite a large impact. So if you don't want to do shading, you can try insulating the roof and have it. If you wanted to, certainly you could change the window sizes, and that's easy enough to do. You can delete these, redraw them, add similar size windows. You can shade them. Something to remember is that it's quite easy to do your standard kinds of shadings on windows very easily by checking this box under the openings tab called local shading. It allows you to specify combinations of things, right? So for example, this one says I can do, here we go. I can do a louver, and all I need to do is to define by just changing the numbers here. I can do side fins, either on the left or the right or both. Again, you've got dimensions, and as long as you specify the dimensions, it will do that. You can do overhangs, so you can add all of these or individually or combinations of them. Now you'll see that this one says locked library data. So I can't change this particular configuration, but I can make a copy of that. And then that copy I can do anything with. So I can rename it, call it something else, you know. So, so let's say, let me say this is an SDI window shade. Okay. And in there, I can change the angle. So instead of 15 degrees, I'll make it 20 degrees. I might decide to put only one fin, left-hand fin, and that you have to do by looking at your passive solar geometry. You can leave the overhang in. You can make it instead of 0.5, you can make it 0.6 meters, for example. And if you apply that, and again, I've selected the first floor, and I've been quite callous about it. I haven't really decided where I should. Those are reasonably easy things to do. You can build a template, and once you build a template, you can apply the template. So suppose I put a template together called, let me call it, just call it copy for now. Then add the local shading, okay? And then you can load the data from the template. You can target whichever zone you want, whichever wall you want, and just click whatever it is that you want to do. So suppose I say on that particular wall, or even if you want on one window. So if I go to a wall which is more than one window, I can actually just pick one and do it. And now let's see if I've got a wall which is more than one. Oh, here we go. So living area, ground floor, this particular window only, I've put the shading device. Okay. So these are all things you can learn. And what will happen is, whoops, what happened here? First floor. Okay, I didn't put it here. Okay, here we are. That's right. And on the ground floor, just let's have a look at it. So you can see it in kind of gray. You can see where the windows are. And what you can also do is if you go to the Visualize tab, you will see it quite careful. So here are the projections that I put, right? And you can see the impact that particular window is having in terms of shading. So it's quite useful to try and do those things. Okay. So if you had lots of windows, you can do some very good shading for certain times of the day and certain times of the year. That's what you need to be able to design. Once you know what you're aiming for and you've got a good design, you can check the impact of that design very easily. Okay, so that's something you want to think about. All right, so I think I can probably leave it at that.
All right, thanks, PC. I will now take up a few questions that we've got. One question is, can we simulate fans and exhaust in Design Builder?
Oh yes, in the air conditioning section, you can certainly do those things.
All right.
So if there are no questions on, are there any questions specifically on natural ventilation? Number one.
There are more questions on shading, I would say, than natural
Okay.
ventilation. Yeah.
Then let's do those. And then
All
I'll
right.
take the air conditioning ones at the end.
All right. Okay. I'll pick up the
Shading
window
questions.
sizing and shading questions now. Yeah.
Hmm.
All right. So one question is, how do we change window to wall ratio for each side, like 40% for north and 20% for south on Design Builder?
Okay, so let's do that. What I'm going to do is I'm going to create a very simple shoebox model, and then play on that. Okay. So we have a series of templates in Design Builder. Okay, and you can, let me change this to Bangalore. So if we run it, then we can do that. Okay. And in those templates, you can, again, pick one that you like. And if you feel that you want to build your own, you can build your own as well. But I will start with that. So we'll build a simple, just a box, and I'll show you. Okay, give it a minute to come up. And when you're using those templates, it's easy to do quick concept type work. Once you roughly know what you want, you may decide to draw custom windows. Okay. So let me draw a box. And then on that box, we'll apply some default windows. And I'll show you where the templates are. And then you guys can explore it a bit more. Sorry, this initialization takes even longer with Zoom. But it'll come up in a minute. And what I'll do is I'll draw a kind of long building which faces long in the east-west direction. So the north facade and the south facade will be long. And then we can have a look at it. Okay, good. So I've got a 3.5 meter high building. I will make it, let's say, 36 meters long. And I'll make it let's say about 20 meters wide. Okay, here we are. If I close off that, now it's coming up with a default set of windows. Okay, I don't know what it is, but that's a template we're using. If I change the template for the entire building, then I can pick templates that are there. So you can see there's a bunch of templates here. Suppose I pick 50% strip window, then it will put that in. Okay, so I got 50% strip. If I want to change one of these, okay, so 0 is north, 180 is south. Suppose on the south wall, I want to put a different template. Instead of a strip, I want to have a window that is 1.5 meters, 30% glazed. So if I do that, then just on that wall, it will change. Okay, so the others are still where it is. You can do that. So that you can do with any orientation. Okay, so suppose this north one, which is 0, I decide that I want a lot of window there. Okay, so I can go find 100%. That's probably too much. Let's say 85% glazing. That's a lot of window, but I can put it, and if you don't like any of the ones that are there, all you need to do is make a copy of something that is close to what you want, and you can change it. Okay, so if you visualize that, you will be able to see all the differences in the windows on each facade. Okay, same sort of thing for shading. You can pick whichever wall it is that you're working on, and on this wall you can put the shading devices that you want. So instead of overhangs, to make it quick, I'll pick one of these standard ones, go back. Okay, so just on that wall, you can see I've implemented everything. If I go to one of the other walls, and I can put something different. So let's try and pick another. Okay, just an overhang. Fine, we'll put that. And so again, you should be able to see on the Visualize tab. This one's got all those louvers and 5 side fins and everything like that. This one's got just the overhang. So if you draw it as a strip, it will put it on the entire strip. If you put it as punched windows, it will do it on each window. And once you turn on the sun, you will be able to see how effective or otherwise it is. You can grab the sun and move it around, or you can type time that you want to look at it. So depending on where you are, you can see here in the summer, it's really quite high in the sky. So the effectiveness of the shading device is really going to be on early mornings and late afternoons. That's when the sun will come into the space. Okay. So if I took a section of this. Now remember, when you take a section off in Design Builder, it actually pretends that the roof is still there and gives you the correct sun penetration. That doesn't happen in all programs. Okay, when you're dealing with Rhino just make sure that it is actually showing you what you want. And by taking a section, it's not actually removing the entire roof. Okay. All right. Other questions? Is
Yeah.
that good enough for your window to wall ratio and shading?
Yeah, I think so. That was good. Thanks, PC.
No worries.
All right. Another question. Are the wind speeds shown in the demonstration dynamic coming from the weather file, or are they
Correct.
taken into thermal comfort consideration in terms of discomfort hours?
No, there's two things going on. What you saw in those arrowheads in red, that is the external wind speed taken from the weather file. Okay. What you saw as arrows coming into the building and out of the building is caused by opening the window and because there is a wind pressure. So the wind pressure then determines how much air is coming in to the windows.
All right. Thanks, PC. Those are the questions we had on natural ventilation and shading. If we can quickly go through, I mean, I don't want to go over time. If it is going to take more than 5 minutes, maybe we could do it the next time also, PC.
What do you want? What do you want me to quickly go over?
Yeah, I think if you could just show where can the students look for the annual cooling load, because I think Mansi talked extensively about it and there are multiple questions.
Okay, so
yeah.
the default setup here is for an air conditioned building. Now, I won't go too much into the detail of that because there's quite a few settings to be set up. Okay. We are working on what is called a simple air conditioning system. So if you look here, HVAC is set to simple. Okay. But if you want to know how it's working, I'm not even going to do any changes. I'm just going to leave everything as a default. But if I run this as a simulation, actually, okay, let me run it. So for this one zone, I'm going to run the full year. And I can show you where to pick the... now, when architects talk about cooling loads, engineers get very upset because when engineers talk about cooling loads, they talk about peak cooling loads. Otherwise, they talk about cooling energy, thermal energy. Okay. I'm fine whichever you choose to do, but just be clear about what you are looking for. Okay. Let me just see. I've just run it for the whole year. I've only asked for hourly and monthly loads. See, these are the cooling loads. Okay. If you want the number is here. You go to table of contents and you go to this annual building performance summary. It will give you district cooling and district heating. These are the thermal loads that an air conditioning system will need to remove from the space to keep the space at whatever condition you have stipulated. So by looking at the result and looking at the activity tab, my cooling thermostat has been set at 24 degrees centigrade. My heating is set at 22 degrees centigrade. It tells me if I want to maintain 24 degrees centigrade during these times, okay, when the air conditioning system is running during these times, how much energy do I need? And that's the energy that I just showed you in the simulation tab. If you go to that ESO file we were looking at, so if I go File, Folders, Energy Plus folder, ESO file, and when it comes up, there are two variables there that are quite useful, especially when you are running it using ideal or simple air conditioning. If you plot the district cooling facility, this is the energy that it requires across the year in terms of cooling. Okay. So what you can do is you can plot the, cancel. Oh no, I want to just delete this variable and I want to plot it on a separate graph because this one is in watts, this is in air temperature. So here you can see that somewhere here, you can see here, these are days when there's a lot of cooling required. Okay, this is the peak cooling requirement. For the whole year, if I was looking at this hour, needed the peak amount of cooling. Okay, so 93 kilowatts for this small building was required. At that time, outside temperature is 32 degrees centigrade. Now you'll notice that there are other days when the outside temperature might be higher, and that's because cooling load is a function of not just air temperature, but also solar radiation, orientation, size of the window, type of the window, construction quality, how many people are there, how much lights are there, how much equipment is there. All of those things go into making up a cooling load. Yeah, I think that's probably good enough for now. We can do in more detail later on. I can see here somebody has said that the losses due to errors and problems while operating the equipment in real life. Yes, this is true. You know, when you model real air conditioning systems, they do come with their own efficiencies and part load efficiencies and so on. And that does make it different from what you just saw. What I've shown you is what, is the thermal loading that you can have by just calculating how much thermal energy you need to extract. You can do fairly complicated air conditioning systems. So I'll just put a very simple, a complicated one. So this one here, it's not an appropriate system for this small building, but you can see here there's a water-cooled chiller, cooling tower, that supplies a cooling coil inside an air handling unit. Air handling unit's got supply fan, return fan, controller, VAV box. So there's a lot going on which you can look at. And it's all possible if you know what you want to do. So you have loops. The loops are divided into supply loops, demand loops, and controls are available for each loop on what you want to do. So there is a controller at this loop and you can set up what it needs to do. So if you know your air conditioning, it's quite comprehensive to do. But in the beginning, to fix up your facade, to your building envelope, to just see how well it is compared to a base case, use the simple air conditioning system. Look at those district heating and cooling loads. They give you the best outcomes. Okay.
All right. Thank you, PC. I think that's all from the questions for today. Once again, thank you so much for your presentation. And I think the students have got a lot of insight on passive design, natural ventilation, as well as a little piece on air conditioning as well, and which we hope to continue the next time. And to all our participants, your deliverable 2 is coming up next week on November 28th. And we hope that you will be able to incorporate all the learnings from today as well in your submissions. All the very best, and we will see you soon for the next webinar. Yes,
So Yashima, I just wanted to say to the students, there are a bunch of YouTube tutorials. If you search in Design Builder YouTube, you will find a bunch of tutorials. Then quickly, the other place you might want to look at to find some options are, if you go to the Design Builder UK website, I'll show it to you quickly. Over there, there's a bunch of webinars and tutorials that are available to you, which you can easily look at. Okay, so just go to the main website. I think this is the right one.
Yeah.
Okay, just go to the main website, look up training, and you will see there's a list of tutorials, and some of them are new. And they recently released one webinar on natural ventilation, which is quite good. I would really recommend that if you're going to use natural ventilation, you should maybe watch that. You'll get quite a lot out of it. Okay, so a lot of resources available to you. Go and do whatever research is required and start using the program.
Absolutely. Thank you so much, PC. All right.
You're welcome.
Bye.
Good night, everyone.
Good night.